Lesson 2, resistance and resistors. Okay, resistance. Ugh. Okay, got that title? Yeah. Yep. Right. Do you know this word? No? Yes? No? Okay, so we'll see. So, another way to think about current, we had charge equals current multiplied by time. But you can also say current equals charge divided by time, which in other words is like saying current is charge per time. Yeah. So another way to think about current is the rate of change of charge per unit time. Yeah. So you can write this one down, and there it is as a formula.
What is the name of the chapter?
Resistance. You got that? Yeah. Now, some more terms. So next one is voltage. Have you ever heard of voltage before?
No.
So voltage might be new. It's what we call electric potential energy per unit charge. So if we just go back to the mechanics for a moment, you know that the ball here has potential energy, which equals mgh, right? In a similar way, the electron or the proton that is moving, it also has a type of potential energy. This potential energy is called the voltage. And the way to think about it is it's joules per coulomb. It's how much energy the charge can do that it has stored in it. So, for example, here, if this has 2 joules per coulomb, then that means whenever we have a coulomb, it can do 2 joules of work. So actually, sorry, I'll do that a little bit better. Okay, so let's say here is 1 coulomb, here is 1 coulomb, here is 1 coulomb, and they're all moving. They can do 2 joules each of work. If I say that the voltage is 2, for example, joules per coulomb. So, if we look here, there's a current going through the projector here. Can you imagine? It comes in, it goes through, and it comes out. So these charges, they're doing work. What work are they doing? Well, they're making the light and they're making the heat. Yeah. So if I said the voltage is 2 joules per coulomb, then that means every coulomb that comes in, it could do 2 joules of work. That's its potential. It could do 2 joules of work. Now that doesn't mean it will do 2 joules of work. It just means how much it could do. Potentially, yeah. So its voltage is like a potential energy. Its ability to do work in the future, maybe. So, voltage is measured in joules per coulomb. But we have a special unit for voltage called a volt. And 1 volt, you can probably guess what you think 1 volt will be. I don't know, not 2. 2 is just my example I made up. 1 volt is 1 joule per 1 coulomb. So these are 220 volts. This here, 220. In your home country, maybe it's 110. Different everywhere. So that means every coulomb that comes out of charge, it could do 220 joules of work per coulomb that comes out. Yeah. Got that? This is something that I forget, and the reason I forget it is because we never use joules per coulomb. They always use volts. But it's worth remembering that 1 volt is just 1 joule per 1 coulomb. Yeah? Let's continue. So, resistance now. So resistance of an electrical conductor is a measure of the difficulty to pass an electric current through the conductor, and the unit is the ohms. So you know this word conductor from chemistry. What's the opposite of a conductor?
Conductor. There is one.
Yeah, come on. Conductor. Unconductor. No.
There is a word.
There is a word. What is it?
Conductor and...
Oh, come on.
Resistor.
No.
No. I remember it.
No, you don't.
Conductivity.
What word are you checking? Which word?
Conductor.
Oh, okay. Do you know it now?
Like the first.
First?
Inside.
The first what?
The leader.
The what?
Will be strong.
Show me. What's the opposite of conductor? Come on. You must remember. You see...
Lead.
No, you see, these are all general English. You want the physics definition.
Vietnamese.
Yeah, hang on. I'll put this down here. Let me tell you.
Oh, the thing is has electric.
Yes. This one. This one.
Yeah.
Insulator.
Insulators. You have to look it up, you cheater. Insulators. Yeah. Right. So, you know that some things are better conductors than others. So, for example, what is a good conductor? What's a good
That
conductor?
conducts electricity.
Yeah. You did this in chemistry. Yeah, give me an example of something.
Gold.
Gold is a good conductor.
Water is a good conductor.
It is not. Water is a very bad conductor.
NaCl.
Huh? Copper is a good conductor.
Sodium chloride.
No, give me a material.
Okay,
Sodium chloride.
No, actually, no, I don't know. I think diamond might be bad.
Metals conduct electricity.
Basically, metals are good conductors. What are bad conductors?
Iron.
Non-metals.
Iron. No.
No. Diamond, graphite.
No, graphite is
Diamond
good.
is a bad conductor. Wood is a bad
Wood is
conductor.
a bad conductor.
Plastic, I think.
Plastic is a very bad conductor. It's an insulator.
Diamond doesn't.
I don't know.
Yeah.
I'm not sure about diamond.
Diamond doesn't conduct.
I don't think so. Yeah.
Because of its shape.
Yeah.
Yeah.
Plastic, wood. These are bad conductors.
Yeah.
So the way we measure how good or bad it is this unit called the ohm. Yeah, omega is the symbol. So the unit is the ohm. Yeah? Can you see that?
Of an electric one.
Do you have that? Yeah. So, what is the definition of an ohm? Let me show you. Continue. Yeah. 1 ohm of resistance means 1 volt of electrical energy was converted into another form of energy. So, let me give you an example here in my picture. Let's say I have 10 volts. So that means 1 coulomb. How much work could each of these guys do? He can do 10 joules. This one could do 10 joules. This one could do 10 joules. Because I said we have 10 volts, for example.
10 over 1.
Yeah. 10 per coulomb. Yeah, 10 over 1. Yeah. Okay. Now, let's say, I don't know, this is a piece of wood, for example. Or it doesn't have to be wood, it could be a light, it could be a TV, whatever. And when they come out, afterwards, they could only do 8 joules of work. So here we have, it's gone down to 8 volts. So what happened to the missing energy? Where did it go?
Goes down.
Yeah, but in what form?
Wood.
What form of energy?
Heat.
Probably heat. So the voltage here was converted into, in total here would be 6 joules. It was 2, 2 and 2 from each.
2 have gone. Like
2 from each have gone, yeah. So this is what 1 ohm, the idea is we lose 1 joule per 1 coulomb. We don't really lose it though, because we can't lose energy. What happens to it? In here, it was converted into heat. Yeah. So 1 ohm means 1 volt was lost, or in other words, 1 joule per 1 coulomb was converted into another form of energy. Usually things like sound, light, or heat. So this definition, 1 ohm means 1 volt of electrical energy was converted into another form when 1 amp is passed through the resistor. Okay. Got this? Yeah? No? Yeah? Okay. Continue? Yeah. Right, so, there is a relationship between charge, current, and resistance. They all have a relationship, and this picture might help you to understand the relationship. It's a very technical picture. voltage, current, and resistance. Here's my picture here. Yeah, you like it? I found it myself. So, I think it helps explain the relationship. The resistance is trying to stop the current going through, and the voltage is what's pushing it through. It's a bit like, how can I put this? You don't want this to be big necessarily, because if this is big, it means he is wasting energy pushing the current. Like this maybe, let's say he is Mr. Coulomb. So he's a Coulomb, we'll say. And this is Mr. Ohm and this is Mr. Volt. So remember I said that if we have 1 ohm, it means we lose 1 volt for each Coulomb then. So basically this is wasted or lost trying to push him through the resistance then. So that's a picture to help you understand the relationship. But we would prefer a formula. And the formula, well actually before the formula we should talk about how to measure it. So how can we measure voltage? Well, we can measure voltage using a voltmeter. Here's a picture of one. You've probably seen them before. Yeah. So
I saw it before.
yeah, I think this is a common equipment in any physics lab. So can you write down its name? It's called a voltmeter. It measures voltage. Just write down voltmeter. Measures voltage. Yeah. So, what unit is amp? Current. It's amps, isn't it? So guess what it's called to measure the current? Yes, it's called an ammeter. Ammeter. The P is dropped.
Oh yeah.
Yeah. You know this one, yeah. This measures current. So what do you think measures resistance? And remember, what's the unit for resistance? Ohm. So we think it should be called an ohm meter. This is an ammeter, by the way, and an ohm meter. They all look the same. This measures resistance, and that's it there. So to measure voltage, we use voltmeter. To measure current, we use an ammeter, and to measure resistance, we use an ohm meter.
Okay, and like what this thing is used for what?
Now we don't actually use this one, and the reason is, if you look please, often we use voltmeter to measure voltage, and often we use an ammeter to measure current, but in real life we don't use usually an ohm meter, and the reason is these machines are actually quite inaccurate. They don't measure it so well. So in real life we don't usually use this one. It's not accurate.
So
But these ones are accurate and these ones are accurate.
okay, the one that is not accurate, why they are doing it?
It's better than nothing.
Yeah, it's
Yeah.
just to experience, just to for your knowledge. I mean, they are just
Like for
Yeah.
it's not accurate, but
it is for taking money.
still something.
It's
You can
still
understand,
something,
you can
yeah.
get some idea.
I mean, usually you just measure it this way to have a rough idea of how much
Yeah.
resistance there is, Continue?
Yeah.
So, we'll not use an ohm meter. In fact, we never use an ohm meter. It's just not accurate. And we'll not study about it. We will use a voltmeter and we will use an ammeter. Okay? Now note, an ammeter requires a current to flow through it. A voltmeter measures voltage between 2 points. Let me explain the difference. So if you want to measure a current, you must put the ammeter in the path of the current. Okay? But if you want to measure the voltage, you connect the voltmeter between 2 points, like this. So the ammeter can give you the current that goes through it, and the voltmeter tells you the difference between here and here. Now please listen, Mahmood, listen. The voltmeter only tells you the difference. For example, imagine that these coulombs have 10 joules per coulomb, and here these coulombs, let's say 9 joules per coulomb then. The voltmeter will display 1 volt. It tells you how much is lost or gained.
But from the
From
10
left to right.
it will be
Yeah.
from the 10 joules,
To the 9.
yes, it will be lost 1.
Lost 1, yeah. That's all it can tell you. It cannot tell you there was 10 here, and it cannot tell you there's 9 here. It can only tell you the gain or loss, the voltage between 2 points. But the ammeter can tell you how much current passes through it. The voltmeter cannot do this. Okay? So please remember that when you're using a voltmeter. Yeah, we say the change is 1 volt between A and B, for example. Okay? So the voltmeter requires 2 points to work. In other words, voltmeters are always between 2 points. And let me draw, and I already drew that. Okay. So again, never do this. Never put the voltmeter in the flow. Okay, it won't work. The only time this works is with using a battery. We'll talk about it later, but really you should not be doing this. Okay, it always needs to be around 2 points. Okay, can you remember that, please? Yeah. Right. So now let's look at the relationship mathematically rather than as a picture. And the relationship between V, I and R is this it's just a simple triangle. So for example, if you want to know what the voltage is, you can know it by saying it's current multiplied resistance. If you want to know what the resistance is, you can know it as voltage divided by current. And if you want to know what the current is, you can know it as voltage divided by resistance. So if you have 2 of these, you can always know the third one. So there is a relationship between the 3, like in my picture. You only need 2 and you can know the other one. Yeah? So please draw this triangle, the VIR triangle. Yeah. This should remind you of another triangle you did in physics. Which one? Distance, speed, time. Yeah. Right. So here's our first example. Let's see, how many have I got? I've got 2 examples. Okay. You can write this down or you can draw it. So we have an ammeter measures 250 milliamps. The resistor is a light bulb. A voltmeter is placed around the light bulb and the voltage measured is 220. You know what, maybe I'll draw that for you, but can you try to draw it and then I'll draw it. I want to see if you can draw this. Little bit of English, sorry. The word resistor means something that has resistance. Yeah. So really everything is a resistor because everything has resistance. We able to draw something? So, this is what I'm picturing. You have a current, and what did I say the current was? 250 milliamps. So the current here is 250 milliamps. This flows through a resistor. The resistor is a light bulb. So this goes through a light bulb. This is a light bulb here. And what comes off of this? Light, of course. And then we'll just draw it like this for the moment. A voltmeter is placed around the light bulb. So around the light bulb here, you place the voltmeter around the light bulb. The voltage is 220 volts. So here we have V equals 220 volts. What is the resistance offered by the light bulb?
Can we divide V divided by I?
That's it, yeah. So if you look here, so here we have our current, comes along, and then what happens when it goes through the light bulb? Does it increase or decrease its voltage? Up or down? Down. How much actually? 220. So, for example, if I had 1 coulomb here, 1 coulomb, how much work did that 1 coulomb do when it went from here to here? No, 220 joules.
Oh.
Yeah. Where did this energy go? It went into light energy here. So there's some resistance here. Some of the energy is being converted into light. There's a resistance here, or from here to here. If I use my triangle, the or equals V over I. This will equal 220 over 250 times 10 to the minus 3. What's that, please? 880 ohms. This is pretty big. It means a lot of electrical voltage energy is being converted into light and heat.
Do we use efficiency with?
Yeah, this will mix into this as well. Yeah. Later, I think maybe.
If I draw the line up
Yeah. You mean if you did it up here?
and this,
Yeah, that's fine. Yeah, it's the same. Yeah. Continue. Yeah. Okay. Right. Yeah, we'll just finish with this one then. So, a 6-volt battery is used in a toy, and the toy has a resistance of 2 ohms. First question, I think you can do this, is what is the current? So, I don't know. We'll have some toy here. Game Boy. Anything. We'll say a Game Boy. Yes? So of course there's a battery here, and the battery goes into the Game Boy and then comes out. What did I say the battery was? It was a 6-volt battery, and the resistance is 2 ohms. So my question is, what is the current here? Is it going to be 3? Let's have a look. VI or V over or is the I. The V is 6 and the or is 2. So yeah, 3 amps is the current then. So that's okay. Yeah, that's okay, isn't it? Yeah. B. If the toy is left on for 1 minute, how many electrons flow from the battery into the toy? Right, so we have to use the other formula. What's that? Q equals IT. What's the I?
The I is
3. And the T, if it's 1 minute, 60. So the answer is 180 coulombs. But that's not what I want. I said,
Divided by.
yeah, how many electrons are there? How many electrons? So yeah, like you said, the number of electrons will equal 180 divided by 1.6 times 10 to the, what's it, minus 16 or something?
1.6 multiplied by 10 minus 90.
19, was it? Yeah, okay, so it's going to be big. What do we have?
Minus 1.125 times 10 to the power of minus 17.
1.125
1.2, yes, minus 17.
minus 17.
Yeah.
Are you sure?
Yeah. 180 over 1.6.
Did you put in minus power minus 19?
Yes.
Let me see.
Yeah, it's 1.125 multiplied by 10 is 21. Yeah, it's not much.
Oh, your brackets. You need brackets, okay?
Yeah.
Brackets.
Oh, okay.
1.125 multiplied
Yeah,
by
21. Okay.
That's minus.
We don't worry about the minus. Really, I should put minuses on the top and the bottom, but we're not worried. Okay, continue?
Yes.
Yeah. Right, I'll let you try the next part for a moment, and then I'll see what you think. The battery is replaced with a 12-volt battery. How does the current change? Hint, you may assume the ore is constant. This is not always the case, and in fact is a law that we'll see in the next class. But for the moment we can imagine the ore doesn't change, even though it sometimes does. So, what happens if we replace the 6 volts with 12 volts?
The I increases if they are.
Yeah.
Well, we have to see, we'll see. Well, we don't know, let's see what happens, let's see. So, firstly, the ore is 2. If I replace the 6 with a 12, I want to know what the I is.
Okay.
So what's the formula for I? I equals V over R. And the V is now 12. And I said the R is still 2. Now in real life, it's not always just going to stay the same, but it's nearly the same. It'd be 6 amps.
Why the R doesn't change?
In real life it does change. It doesn't change much though. We'll see this in the next lesson. If these numbers are small, then the ore is something that doesn't change much. It kind of stays the same. But in fact that's a law that we'll see in the next class. The ore really does change though. It really does change. In fact the ore increases, but it will only increase a little bit, like maybe 2.1. We'll say it's roughly the same. So yeah, the current would double. Yeah. Okay. Right. So again, I think if you just want to make note of these, if you want to, or if you can just watch the video, that's fine too. They won't take you that long to do because they're all pretty straightforward. Yeah. Are you going to watch it on YouTube or are you taking a picture? Moodle, I mean, yeah.
We have two homeworks or?
Yeah, you have this lesson number 2 in mechanics.
Yeah.
The first homework you finished in class.
Oh.
So it's just this one for electricity.
And of course.
So
Yeah.
this one we will make as a homework
Yes.
and when we go home. Okay.
Yeah. Homework when you go home. Don't give me a hard time. I'm hungry, okay?
All of us. And I did not take my break.
Big mistake.
No problem.
I'll take that on Friday's class.
Monday.
Because Monday's class, because I want to make a folder to put them in. I don't have any folders.
I have a notebook, that's fine. You want me to?
I just
Separate place.
Okay.
I just want to take what you've been doing for that week, that's all. But you're writing everything in a copybook, so
Yeah.
that's fine, you can leave it in that, yeah.
Uh-huh.
yeah, let me just close this.